In the name of God, the merciful, the compassionate. Hi, my dear friends, and welcome to the first official lecture of software testing. In this lecture, we talk about the philosophy of software testing according to the first chapter of my textbook. As I mentioned before, as I introduced in the previous lecture, my textbook is Introduction to Software Testing, second edition by Paul Amann and Jeff Afford. Today, in our civilization life, we get several services from different providers, such as transportation system, educational system, financial and medical infrastructures. And as you know, software is an essential component of this infrastructure. So we could say simply, software is a skin that surrounds our civilization. Testing in the 21st century. Today we are in the beginning of the third decade of 21st century. We know that software defines the behavior of all information and communication infrastructure, as I mentioned in previous slides, and this shows that today's software market is much bigger than ever. It's more competitive due to the same provider try to their best on the same product, and eventually this market has more users. On the other hand, you know the role of embedded control applications in our life. As we've seen in our environment, systems such as airplanes controls, air traffic controls, and other devices such as watches, ovens, remote controllers, cell phones. In all of these devices, the main functionality of them is defined by a software component, and this component is vital for functionality of these devices. And in software engineering methodologies, you know that agile processes try to deliver software components as soon as possible in software development lifecycle. So this causes put increased pressure on testers, and programmers must do unit tests themselves who are not trained enough for software testing. On the other hand, in the requirement document of software products of systems, there are several functional requirements. All of them should be covered by the product, and this would be validated by software engineers. So tests are key to guarantee the functional requirements of a software product, but there are several questions, such as how many tests are enough for testing a typical product, what tests are good for this product, and who builds those tests, and so on. As you know, software quality today is increasingly become essential to all businesses, and we could not neglect these questions. So knowledge of software testing is becoming necessary for all software engineers. In this course, we would learn you to do software testing and learn the fundamental basics, fundamental rules in software testing, which leads to a high quality collection of tests for a typical software product. So industry is going through a revolution in what testing means to the success of software products. But fortunately, a few basic software testing concepts can be used to design a test for a large variety of software applications. So I hope I can properly learn you how to use these basic concepts in software testing in this course. First of all, we define three concepts in software testing texts, which are used commonly, very common in software testing documentation, that includes software faults, software errors, and software failures. What is a software fault? We define a software fault as a static defect in the software. For example, suppose to this method, the sign-up method. In this method, an integer value x is passed as an input parameter of the method, and the method should detect the sign of its input value and return the sign of this input value as a string type. In the first statement of this method, you see that a variable sign is defined of type string, and in the next statement x is compared with 0. If x is less than 0, the sign should be set to negative string correctly. But in else statement, you note that the sign is set incorrectly. The sign is set to negative instead of non-negative string or positive string. In the last statement of the method, the return sign is done. You should note that the faulty statement, the defect in this method, is the statement of the else part of the method. Sign is set to negative in this statement, and this is a static defect. This defect exists in this method permanently until I would fixes it manually. The other concept in software testing is software failure. What is software failure? What's the difference between software failure and software fault? We define software fault as a static defect, but what is the software failure? We define software failure as external incorrect behavior with respect to the requirements or other description of the expected behavior of the program. Please note that we have two different terms in software testing, means expected result or actual result and actual result. What's the expected result and what's the difference with actual result in this context? In design documentation or in a requirement documentation of a software, we define the functionality of each method of the software elaborately, so that we define the output of each method for each type of its input, each boundary of its inputs. So this definition is expected result of these definitions are expected results of a method. But when a method call is happen, but when we call a method for a concrete input, we receive actual result after its execution. For example, in this case, in sign-off method, when we call sign-off for values such as -2, by execution of this method, we receive negative string. This output value is an actual result of the sign-off method, of execution of the sign-off method for -2. So when the actual result is the same with expected result, which is defined in design documentation, in design phase of the development, we say there is no software failure. But when these two is different, when the actual result and the expected result is not the same, for some execution we see a software failure, we experience a software failure, we see an incorrect behavior of the software. So the software failure is defined as an external incorrect behavior. In the simplest form of this definition, we say that the expected result is differ with actual result. Okay. But when there is a question, when software failure happen, it's obviously that a software failure is the result of the execution of a faulty statement in our program. But when a software fault, when a faulty statement leads to software failure. To answer this later question, we should define another term which is software error. What is a software error? We define software error as an incorrect internal state of the program. What is the internal state of a program? The internal state of a program is defined by the values of its internal variables. For example, in this sign-off method, we have just one internal variable, the sign variable. If this variable is set incorrectly in some part of the method, we could say that the program, the method, went to an incorrect state, internal state, because the internal variable sign set to an incorrect value. Incorrect internal state is defined by both internal variables, both values of internal variables of a program and values of internal registers of the CPU, such as program counters, such as data register, such as instruction register. Okay. We summarize this definition. The software error is defined as an incorrect internal state that is the manifestation of some fault. But there is a question when a fault leads to software error, and when a software error leads to software failure. Actually, software fault causes a software error, and software error could cause a software failure. But when faulty statement of our program leads to software error, please note that when we execute a faulty statement in our program, and in this faulty statement some of internal variables get incorrect values, we say that the software fault leads to software error. The faulty statement causes a software error. Okay, but when a software error causes a software failure, you should note that any incorrect values of internal variables propagate across the execution path of a program so that it can cause an incorrect final state for the program. When a software error state propagates its incorrect values across execution paths until affecting the final state of the program, and the incorrect part of the final state of the program is showed for the user, we say that the software error leads to software failure. I repeat it again. Note that when a software error state, when the incorrect part of error state propagated through the execution path until it affects the final state of the program, and the incorrect part of final state showed to the user feels an incorrect behavior and a different behavior of the program. So the end user feels a software failure. Okay. The last point in this slide is as you know, software does not degrade it. Software products does not wear out. So there is a difference between software faults and faults in other products such as hardware products. We say that software faults are equivalent to design mistake in hardware products. As you know, hardware faults could be the result of wearing out or degrading of some components of hardware, or it could be the result of a design mistake. But in software products, the faults is just equivalent to design mistakes in hardware products. For more illustration of the difference between faults and failure and error in software testing, an example is showed in this slide, is presented in this slide. Suppose a patient go to the doctor, and the patient gives the doctor a list of symptoms such as headache, such as fever, sore throat, and so on. These symptoms actually are failures in the body of the patient. The doctor, after hear the symptoms from the patient, tries to diagnose the root causes, the faults of the body in the body of the patients, or the ailments of the patients. So the ailment is equivalent to fault in software testing, in software projects. For diagnosing the root cause of the ailment, the doctor may look for some anomalies in internal state of the patient, such as high blood pressure, irregular heartbeat, bacteria in bloodstream. These anomaly conditions is equivalent to error states in software products. The anomalies conditions in body of the patient is equivalent to errors in software products. So in our biology, faults could cause errors in our bodies, and errors could lead to failures. Okay. But there is a difference between software fault and medical problems for our personal bodies. Note that most medical problems result from external attacks, such as bacteria, viruses, or physical degradation as we age. But as we said in previous slide, software faults exist originally, were there at the beginning and do not appear when a part wears out. Actually, no part of the software product wears out. Okay. This slide shows another concrete example in software context. Look at this method, non-zero method. This method gets an integer array as its input, and it should return the count of occurrences of 0 in the array in its input. This method should throw null pointer exception for null input, and in other situations it should be return the number of occurrences of 0. For these aims, in the first statement, a counter is defined and initialized by 0 correctly. This variable counts the number of occurrences of 0 in the array. And next, we should scan elements of the array one by one and check if there is a 0 element. If there exists a 0 element, count variables incremented. So we use a for loop and a counter for the for loop. Integer I is initialized by 1 until there is an element in the array. We continue to checking element by comparing element by 0. If the element is equal to 0, we incremented the count variable, and finally after scanning all elements of the array, the count value is returned by the last statement. There is a faulty statement in this method. But what is the faulty statement? What statement in this method is false? Do you know? As you know, arrays in some programming language such as C++, such as Java language, started from 0. Array indexes started from 0, not in 1. So this initialization is wrong. Initialization of this counter I is wrong. It should be started from 0 instead of 1. So the statement is a faulty statement in this example. Suppose we are trying to test this 0 to diagnose faults of this method. At first we test this method by this array. In this array there is 3 elements and the last element is 0. When we want to call the non-zero for this array, we expected it returns 1. So the expected result is 1. And when we executed, we call this method for this array, we see the return value, the return count as 1. So the actual value is 1 again. Because when we execute this method in the for statement, we start from position 1 of the array. The first element is not checked. There is no problem in this case because the first element is not 0. This doesn't lead to failure because there is no 0 element in the first location. So we start from location 1, from index 1, and compare 7 by 0, and we see that it's not 0. In the next execution of for loop, we see an element 0, the count is incremented from 0 to 1, and finally return 1 as its output. So the actual result in this case, in this test case, we name this a test case. Each test case has several parts. One part of the test case of our test cases is input data. The input part of this test case is the array with 3 elements. Another part of the test case is expected result. The expected result is 1. And the actual result we have seen is actually 1. So in this case, we don't feel a failure in execution of this method because the actual result and the expected result is the same. But what about error? Are we experience an error state in execution of this method? Yes. Yes. In the first round of execution, the for statement, the internal I variable should be set to 0, not 1. So the first statement we pass in this execution is an incorrect state, internal state. So we have experienced an error state in this execution, but this error state does not lead to software failure because its incorrect internal variable do not affect the final state of the execution. The final state of the execution sets I to value 2, index 12. The array, this is correct, and the value of count also correct. So the the first error state do not propagate through the execution path and do not affect the final state of this method. So this error state doesn't cause a software failure. We have no software failure in this test case. But look at this test case. How about this test case? This test case includes an input data, an input array with 3 elements, just the elements located in the first test case, but the order of them are changed. In the new test case, we have a 0 element in the first position of the array. So as we've seen, the first position of this of the array is not checked by the for loop, and the internal state and the first error state would be published, would be propagated across the execution path. The result of this error states would be propagated during the execution of this for loop, because in the first execution, first round of running for loop, the count should be set to 1, but this isn't done because the for loop starts at position 1 and the first element is not be checked. So this error propagates during the run to the variable code. The error state affect the count variable, affect the final value setting in the count variable. So this causes a software failure. The final return value is 0 instead of 1. So that we see actual value as 0. This is not the same as expected. One. So we feel a software failure. Count is 0 at the return statement. So we summarize this problem. Not all executions of a program shows failures. In software testing, we try to design tests that could show failures. Good tests are those that can show failures. Tests that are not that could not show failures aren't very important. So we try to design tests that could show failures. But for doing this important work, we should learn a lot of rules, a lot of principles in software failures, which is learned to you in this course. Okay. The other term that is using informally in some text, some informal text and informal speakings is the term bug. The term bug sometimes used instead of fault, sometimes used instead of error, sometimes means failures in informally speaking or informally text that's published daily in software testing concepts. This term are not meaningful in engineering or technical texts in this area, and this class will try to use words that have precise, defined and ambiguous meanings, such as fault, error and failure, and we don't use bug in this course or in this textbook or in other textbooks, but there are some historical documents, such as documentations of Thomas Edison and other scientists that uses bug, but today we use just fault, error and failure with the mentioned meanings in previous slides. And in the next slide, we see some spectacular software failures in recently decades of software products, such as NASA Mars lander, Track 25 radiation machines, and Ariane 5 explosion. For example, note that in Track 25 radiation machine, poor testing safety critical software causes to kill 3 patients at the first usage of it. This is because of a software, just because of software failure. A software failure in its controller, in its embedded control application. Or in NASA later, also the software failure caused crashes due to a unit integration fault. The software failure in Ariane 5 led to an explosion just after flying because of a bad digit conversion, and causes a $320 million loss. There are several examples of this type in the literature. You can search and study them, what happened in recent years because of software failures. So we say that we need our software to be dependable, and dependability testing is one way to assess dependability. You should note that testing could not guarantee that a software product is fault-free. This is important. You should note that testing could not guarantee that a software product is fault-free, but it tries to find more faults in software product. It gives us more confidence about the product. This is one of the many tools, many approaches that is used for that are used for assess dependability. As another example of the catastrophe happening in by software failure is the Northeast Blackout in 2003 in America and Canada, which causes 508 generating units and 256 power plants shut down, and this affected the life of 10 million people in Ontario and 20 million people in 8 US states. And the financial loss is about $6 billion. When they checked the root cause of this happening, they received that a software failure is happening in the alarm system in the energy management system. And this blackout continued in some parts of these regions for about a week. So this is a bad catastrophe. In the literature, there are several reports that show the cost of software failures in recent decades. Some of them reported by the NIST Institute, some of them reported by Forbes and McAfee and etc. You can search these documentations, and you can study these reports and see what's happening in software products recently. Also, this slide shows some of the software failures that causes more fatal happening and a large monetary losses in all over the world due to these failures. So software testers try to find faults before the faults find users. This is an important sentence in this slide. Software testers, what is the work of software testers? What is the responsibility of software testers? Software testers try to find faults before the faults find users. In these cases, faults found its users. So we summarize this talk about the importance of software testing in 21st century. As we know, there are more safety critical systems in our world, and real-time softwares, the embedded softwares, has a unique role in our life. And you know that enterprise applications today is more bigger than ever and has more users, and free software increases our expectation from the software products, and security is a notable challenge in software products to the reliability, other quality attributes such as maintainability, testability, availability, and scalability is some of the attributes that should be guaranteed by today's software product. But for guarantee these attributes, we should learn some rules, some fundamentals, and we should learn software testing in an engineering manner in our academic education programs. So this course continued with this goal. I hope at the end of the course we got my goals and your be satisfaction for this course. But what about cost of not testing? Can you tell me what is the cost of not testing? Also, you have seen in the excuse me for pausing the recording in this slide we say about what is the cost of not testing. In the first statement, it's correctly poor program manager might say testing is too expensive, and they plan for not testing. Actually, testing is the most time-consuming and expensive part of software development. This is true, but as we saw in previous slide, not testing is even more expensive than testing. So we should testing enough our software product to have an acceptable quality and prevent some catastrophe happening. If we have too little testing effort at early stages of software development, the cost of testing actually increases. We talk about this sentence in the next slide by some reports of one of the known institute at Carnegie Mellon University. And the last point is planning for testing after development prohibitively expensive. This is just this is true also, and I will talk about this in the next slide. Look at the chart of the mentioned report. This chart is reported by Software Engineering Institute of Carnegie Mellon University. This is a real research. This is the result of real research. This funding is could be dependable, and we talk about the last 2 points in the previous slide. Please note that in this chart the yellow bars show fault origins. As you see in this chart, approximately almost of software faults originate from the 3 first stages of software development life cycle, such as requirement analysis stage, or design phase, or implementation phase. So you should note that if we could prevent faults in this stage, in this first stage, we don't have side effect in the later stage of software development life cycle and in post deployment phase. So please note the fault detection capability of software engineers is in different phases of software development process. The green bar shows the fault detection, the amount of fault detection in each stage of software development. At every stage we could detect some faults in our software product, but the faults that is detected after deployment of software is very costly faults. For this, you should see the red bars. The red bar shows the unit cost of the faults detected at each stage. Faults detected in the post-development stage is more costly than the faults detected in previous stages. So we should try to detect faults in phases previous the deployment of the final program. Especially we should try to detect faults in the first 3 stages, because the faults detected in these first 3 stages has a little cost and could be neglected in the cost of overall cost of the project. So in software testing we try to design test cases as early as possible in software development life cycle, and we try to do the testing as soon as possible. We summarize our talking in this lecture, this slide. The first question and the title of the chapter is why do we test software? At this point, all of you know why we do the software testing. As tester's goal is to eliminate faults as early as possible, and this could improve the quality of our software product. This could reduce the cost of our projects and preserve customer satisfaction. I finish this lecture at this slide, and this is the last slide of our chapter, our first chapter. I hope this lecture would be proper enough for you. I wish you have good days. Goodbye. See you next session.